Hello, everyone, and welcome to today's edition of our extremal and probabilistic combinatorics webinar. Before we start with today's talk, let me go through the usual technical stuff. This talk is recorded, and so will be your questions. If you ask them during this main session, there will be an unrecorded part at the end. So please bear that in mind. If you have any question during the talk, please just unmute yourself and pose the question. If your audio is not working, just type it in the chat. Maybe someone else will answer that, and if not, then I will interrupt the speaker and read the question out. And I guess we can start. So with Ferenc bench from the Chen Institute in Budapest, and Ferenc will talk about some recent results of his about atoms of the matching measure. Okay, and if you want, you can go on the seminar webpage, and there are his slides, even though in a slightly different variant, are accessible there. So, Ferry, please.
Yeah, thank you. So welcome. Today I would like to speak about the matching measure, and first of all, I would like to introduce you this notion, which was invented by Albert Csikvári, Frankel, and Kuhn. And then by investigating the atoms, we would like to see how does it relate to other classical results what we know. So I have to say beforehand that this whole work is a joint work with András Mészáros, and our main goal was to really just understand the atoms of matching measures of random rooted graphs. And so now, first of all, I would like to just give you the definition. So to define the matching measure, there is an easy way and there is a motivating way. So I will now give you the easy, short way to define it. So I will need a graph which is called the path tree, or sometimes called the Gaussian tree, or in physics it's called self-avoiding walk trees. This is nothing else that if you ever have a rooted graph GO and you consider all the passes that starts from that vertex, you can build a tree on those passes by connecting two paths if they are consecutive extension of one of them is consecutive extension of one of the other. So, for example, in this image, you can see that on the right, you see the passes starting from the vertex 1 on the left. Okay, and easily, if you have 1, 2, 3, you can read as a subpass here from starting 1, 2, 3. Okay, this is a well-defined object also for infinite graphs. Here I don't need to specify is it a finite graph or not. We only have to specify a root for this construction. So now here's the definition. The matching measure of a rooted graph GO. So I will say rooted graph when there is a specified root for the graph. The spectrum measure. The matching measure will be exactly the spectral measure of this path tree where we choose the root to be O. In a different way, if you don't like this kind of definition, this is the same as saying that this is the unique probability measure in minus dt, such that the case moment of this measure is exactly the number of closed walks in the path tree starting from O and finishing at O. Okay? Or a third way to say that the case moment of this probability measure is nothing else but the diagonal element of a to the k at 0, position. Okay, and yeah, d is the largest degree of the graph. This is fixed for one for all. So, so this is what I defined the matching measure for rooted graphs. And clearly, if we have any kind of probability distribution on rooted graphs, then we could define the so-called expected matching measure that will be nothing else, but we are taking the average of the rooted matching measures. Okay, so you can already see here at this moment that if I would say that G is a tree, then this matching measure nothing else but the usual spectral measure of trees. And already there are a lot of works that already considered spectral measures of trees. They try to understand the behavior of the spectral measure of the trees around 0, also at 0. And there are several works. So, for example, there is the work of Boltzmann and Salez. They investigated the atom at 0 for unimodular random trees, and also there are several others, so by Salez, Boltzmann, Chen, and Virag, and so on. So, in some sense, you can think about the matching measure as branch 2 generalization of spectral measures for non-trees. Okay, so for trees it coincides with the usual spectral measure, but for general graphs it's different. Okay, so here's the motivation. You may wonder, why am I calling them matching measure? There is no matching in the previous slide. So in order to answer that question, let me recall the definition of Hammond-Lieb for partition function of monomer-dimer models, in a different way to say the matching polynomial that is the generating function of matchings in a finite graph G. Okay, so this makes sense only in finite graph. And already when they defined this polynomial, they investigated a lot of nice properties of this partition function. And one which is quite important for us is that all complex zeros of this polynomial lies in a bounded interval, and you can say this bounded interval is minus dd. Okay, so this polynomial has no other, it doesn't have real complex zeros. Okay, so right now I could define a new measure, which is the matching measure. This makes only sense for a finite graph, that I will take a uniform random zero of this polynomial. Okay, so I take the average of the direct mass on the zeros of this polynomial. This will be a probability measure in minus dd. Okay, and how is it related to the previous matching measure? For that, we have to think about how can we turn a finite graph into a randomly rooted graph. The easiest way to do is that we just pick a random, uniform random vertex from the graph G, and we will call that the root. Okay, so in this way, we can turn any finite graph into a random rooted graph. And due to Godzilla, in this language, if we just translate his result, he just proved that the matching measure, so this finite graph, that nu hat G, is exactly the expected matching measure of this randomly rooted graph. Okay, so so this is the main motivation for the name. So this is called the matching measure. So this is what basically this is what we took as a definition for general graphs. Though and when yeah, so this measure was introduced by Albert, Chikvari, Frenkel, and Kuhn, and they did it in a successful way because this measure encodes a lot of matching-related parameters. Okay, so for example, this number of all the matchings or the growth rate of all the matchings, and this kind of quantities is already encoded in this measure. Out of all of these, I would like to just recall one important thing here is that what can we say about the measure of the zero for this matching measure? So if the measure of zero is positive, it means that the matching polynomial, what I just defined here, it has no constant. Okay, what does it mean it has no constant? It means that the lowest power of z is positive. In other words, the largest m size, so the largest matching what I can choose, it will not able to cover the whole graph. Okay, so in other words, G has no perfect matching. So seeing an atom at 0 is the same as saying G has no perfect matching. Okay, so so we see that already the atoms encodes this, the weights of the atoms encodes this kind of information, and because of this previous average definition, we can rewrite the atom of the matching measure as the average weight of the rooted matching measures. So in other words, every vertex has some contribution into the weight of the matching measure. So importantly, if this quantity is positive, it means that there has to be at least one vertex where this new GO measure will have positive measure on the zero set. Okay, so this kind of vertices will be really important for us, and this is why we name them. So we will call them as theta essential vertices. So we will call vertex theta essential if he has a positive contribution into the spectral measure. Also, we will call a vertex to be special if he is not essential, but if he has an essential neighbor. And we will call the graph to be critical if all the vertices are critical. Now you might get familiar with, you might see something similar. You already saw something similar diagram in your life. This is the Gallai-Edmonds structure theorem. So this Gallai-Edmonds structure theorem, the classical one, is about matchings, and it was generalized by Pu and Chen for any theta, and it has the following. So if we ever consider all the essential vertices in the graph G, and we denote them by D, this is the red graph here, and each connected component is denoted by this ellipse. The special vertices are this black part here, and the rest of the graph is this C. Then the structure theorem tells us that all connected component of the essential part is critical. Okay. Another, the size of the atom at theta will be exactly the number of connected components of the essentials minus the size of the special vertices divided by. Okay, so out of this structure, we can read out this quantity. Also, if we restrict our graph to the lower part and we took any vertex there, it will be not essential. Okay, and if you specialize to theta equals 0, then this is what is the classical Gallai-Edmonds theorem that gives you that whenever you have a maximum matching, then the matching definitely will cover all vertices in A union C, so this part is matched. Also, A is matched into D. Also, any connected component in D has at most one uncovered vertex, and also there is at most one matched edge that goes to A from any component from D. Okay. So maybe I should say that, yeah, maybe that would be better. So you can think when theta is 0, you can think about this nu GO 0 as a quantitative measurement for am I being, is there a maximum matching that leaves me uncovered? Okay. For theta equals 0, this is the meaning of this essentiality, and this is what we usually you learn. Okay, so this is the theorem that we were partially generalized for infinite graphs, but immediately you can see 2 bullet points that is not true, or at least there will be some problems to define it. So one easy to go is the second. So for finite graphs, it makes sense to define this expected or this matching measure. But when we have infinite graphs, how to define this object? We cannot choose uniformly randomly a vertex from an infinite graph. So we will need some condition on the random rooted graphs that will place the role of finiteness. Okay, this property is called the unimodularity, and also for the fourth, what do we call maximum matching? So there you can define different ways what we would call maximum matchings, and it might happen that it will not resemble these definitions of theta essential and theta special. So it will not respect this decomposition. In order to replace this maximal matching, I have to speak about Boltzmann random matching. What you have to bring with you from here is that for any graph, any positive t, you can define a unique probability distribution on the matchings of the graph, such that on each cylindric strat, you are defining these probabilities using finite exertions. And a theorem of Bordenav's, Lillage, and Salez is that this definition doesn't depend on the exertions what you are choosing. So this is really there exists a unique random matching. Okay. So, and what we will do is the Boltzmann random matching at temperature 0. This will be nothing else, but we are taking these matchings and we are cooling down the temperature. And what we will get as a limit, this is what we'll call the Boltzmann random matching at temperature 0. Okay. So as you can already guess that we have this nice physical view for matchings that there is a temperature parameter t, and the maximal matching will correspond for the zero temperature Boltzmann matchings. At least for finite graphs, you can easily see that really gives you back uniform random maximal matching in the graph G. Okay, so if you let t goes to 0, this probability distribution on the maximum on the matchings will converge to a uniform random maximal matching of G. However, for infinite graphs, we know there exists zero Boltzmann random matching at temperature 0, but there might be more, but we were not able to prove there any of these statements. So is there unique? Are they unique or or there are several ones, but we think there are more for general graphs.
So fair, just a notational question. I think this is normally called maximum, right? Matching, which is you know, the set of matchings of maximal cardinality. That's what you are talking about, right?
Yeah, maximal cardinality.
Maxim. So, but it's, yeah, okay, which I think is called maximum. Okay, thanks.
So, as I promised you, so we obtained partially the generalization of the Gallai-Edmonds structure theorem. So we have again the same picture, and now assuming G is an infinite graph. What can we say in this case? We can say that any connected component of any connected component of the essential part will be theta critical. Okay, what can we say about when we are specializing to 0? Then in that case, let M be any Boltzmann random matching and temperature 0. Then with probability 1, the same statement holds. Okay, with probability 1, A and C will be covered. A will be matched into D. There is at most one uncovered vertex in GD, and at most one vertex of the component is matched into A. So these statements hold with probability 1. And as I also promised you that if we have to replace the finite graphs, the convenient way to replace it is to say that we have a random rooted graph, which is unimodular. And in that case, we were able to prove that the atom of the expected matching measure is upper bounded by the number of, saying that the number of components in the essential part minus the probability that I am special vertex. Okay, so this first part is just roughly. Okay, so it really resembles that, but instead of having equality, we have inequality. But tell the truth, at theta equals 0, we have equality. Okay, so so this kind of decomposition theorem, what I just described you, it has some nice corollaries, or you can say that the next statements can be proven separately. Is about whenever we have a infinite connected vertex-transitive graph. Okay, what we were able to show that none of the vertices is essential. Okay, so if you like to say in matchings and theta is 0, then it means that any infinite connected vertex-transitive graph has a matching. Okay, so this theorem was already proved in finite case for Ku and Chen, but you know, in the case of finite graphs, it's a little bit different because you can see only atoms. So the statement there is that the size of the atom at theta is 1 divided by n. Okay, this and Aubert, Chikvari, and Hubei, they were able to prove the same statement under the assumption that the infinite graph is a limit of finite vertex-transitive graphs. Okay, so they obtained the same results. So we were able to generalize these. And another extension of the same theorem is that when you are throwing away the vertex transitivity, so now you are saying that, okay, I would like to allow something more randomness. The next good candidate to look at is the unimodular random graphs. And what we were able to show that if this unimodular random graph has a nice expansion, okay, it's ergodic non-amenable, then it will have only finitely many atoms in the expected matching measure. And this theorem was proved by Salez for unimodular random trees. So these kind of informations are encoded in the atoms of the matching measure. And so for the rest of the talk, I would like to give you the IDs and basically the main tools how to investigate the atoms. Okay, how to understand how to understand what's happening with the vertices, how to distinguish them, and so on. And hopefully at the end I would like to put together these tools to prove, for example, prove this infinite connected vertex-transitive statement.
So, Ferry, Julian is asking if you could remind the definition of theta essentiality, and my question also would be if you could relate the property of being an infinite vertex-transitive graph versus being a limit of finite vertex-transitive graphs.
Sorry, the first question I didn't hear.
So Julian is asking whether you could remind the definition of theta essentiality, and I'm asking how does it compare to be infinite vertex transitive versus a limit of finite vertex transitive?
So for infinite vertex transitive graph, so a priori, it's a bigger set of graphs, so you can easily define. But I'm not sure that every vertex transitive graph. I think almost true. So not every vertex transitive graph can be obtained as limits of finite vertex transitive graphs in local sense. So, for example, if you think about groups, it would mean that, yeah, for example, if the Cayley graph, so the group doesn't have any finite quotients, then you cannot get the Cayley graph. And for the essentiality, I will just, I think, go backward. No, that's too long. Yeah, sorry, here's the definition. So the essential means that the matching measure at the set theta is positive. Okay, in other words, there is an atom in the matching measure of GO. Okay. If you are not, if you don't like this kind of definition, there will be two more for this.
Okay, thank you. I'm just wondering, how do I think about that? Yeah, I'm just a bit confused by this definition still. What is there an easy combinatorial way of thinking about that, or yeah, I'm just a bit confused by that definition still.
How to say? So if you're just think about the zero, okay, so the zero being atom, it means that there is a maximum matching that that leaves me uncovered. Okay.
Right.
This is a good image to have in your
right.
Okay. So, but I hope there will be some one more spectral definition. I hope that will help. Yeah, I hope. So, okay. So, what about what is our strategy? So, the strategy to understand of this kind of, or to understand this to attack these statements, it relies on two pillars. First, we want to understand that if we delete a vertex, how does this essential vertices changes in the graph? Okay, how does this property, how stable is this property to being essential? Okay, the second is, can we have any control on how does the change, the weight of the atoms changes by vertices? Okay, so the first is more like what's happening with the vertices, so what's happening with these properties to being essential, not essential. The second question is more like quantitative. Okay, so can we associate some quantitative change for deleting vertices? And the main tool to attack this is the Stieltjes transformation. So what is the Stieltjes transformation? For any probability measure, you can define Stieltjes transform. This is just the integration of z minus x inverse. Okay, but since all of these measures arises from bounded operators, we can use spectral theory to express the same function as what you can see here. This is the z minus a inverse times Q O, so the diagonal element of O. Okay, and if you like the finite finite word, this function is nothing else that you take the matching polynomial, you delete O, and you divide with the original matching polynomial. This is the same function for finite graphs. All of these are the same. And why do we like Stieltjes transforms? Because they seize the atoms. Okay, you can express the atoms using the Stieltjes transforms. Okay, what do I mean by here is that the size of the atom, it can be read out as IT times the Stieltjes transform when t goes from the complex plane perpendicular to theta. Okay, and again using spectral theory, because we have nice bounded operators, we can also express this quantity as the orthogonal projection of key u into the theta eigenspace, and we look at the u's coordinate of it. Okay, so this pi gu is the orthogonal projection of the adjacency operator into the theta eigenspace. Okay, this is what we get for free from spectral theory. So this so the first is because it's a Stieltjes transform. The second is because spectral theory. So, and unfortunately, we will need more. We have to define the Stieltjes transform for more vertices other than one. So for any finite set of vertices, I will define the Stieltjes transform as product of Stieltjes transforms. We are just telescopically, we are putting one more vertex always in. This is a well-defined thing, so it doesn't depend on the order on the vertices. And moreover, if this set of vertices form a path starting from U, then we can define, and now it's a little bit miracle at this moment, that I can define this new GP theta. Okay, so what is the contribution of the path to the atom theta? And we can define this as a limit here. And this is the same by spectral theory. Then we take the projection of the vertex U into the theta eigenspace, and we look at the piece coordinate of it. Okay, so this is one of the lemma which helps us to calculate with Stieltjes transforms. The other lemma is this. And I think this is quite familiar for everyone, because what does it express? It expresses the easy thing that either a matching leaves me uncovered. In that case, the matching is a matching in G minus U, or I am matched to one of my neighbors, say to V, and the rest of the matching is a matching in G minus UV. Okay, and this easy observation is encoded in this lemma. Okay. If you like, you can take the finite word definition of the Stieltjes transform, and by dividing here with mu g z, you will obtain this this lemma here. Okay, so you can convince yourself that this is true. Okay, so these are the main recursions for Stieltjes transforms. And now back again. So we will distinguish essential vertices. Now I will use the Stieltjes transform notation. So we will call a vertex to be essential if it has a positive weight at the theta. Okay, so in other words, the Stieltjes transforms has a pole there. And for non-essential vertices, we will introduce two more classes. One of them is called positive, the other is called neutral. Okay, we will call a non-essential vertex to be positive if this quantity, this quotient has a positive non-zero limits, and it is neutral if this this quotient has limit infinity. Okay, and for the rest, we will call special vertex if someone is non-essential, but it has an essential neighbor. Okay, so a priori, special vertex can be either neutral or positive. So this is the definition what I will use now on. Okay, so right now everyone might wonder about what is this quotient? What does it expresses? And turns out that it's expressed something interesting. It expresses that what is the contribution of the neighbors of U in the deleted graph. Okay. To be precise, it is the inverse of that. Okay. In particular, someone is positive. Just to recall, it means that on the left-hand side has to be positive. That can only happen if the right-hand side, on the right-hand side, there is at least someone who is positive. But one of the expression has to be non-zero. Okay, but what does it mean? It means that U has a neighbor V such that V became essential after we deleted U. Okay, so this is the meaning of positivity. So positivity means that if you delete him, there will be a neighbor who will become essential. Okay, and the proof of that is simply we have to use the previously mentioned lemma. We just put theta plus it, and everything will work out by taking limits in both sides. So as I told you, we would like to understand first what's happening if we delete different type of vertices. Now we have 3 types of vertices, and we would like to understand what's happening with the rest. And the first tool is to speak about essential passes. Okay, essential path is like the generalization of essential vertices. It means that this new GP at theta is strictly positive. Okay, so if you like the spectral way to say that the orthogonal projection of Q into the theta eigenspace at coordinate P, it is not zero. Okay, the claim, whenever you have such a path, both endpoints has to be essential. Why is that? It's quite simple, because if we would assume that the starting vertex U is non-essential, then by definition it means that if it is not essential, then the atom has to be zero. But the atom is zero means that this scalar product is zero. So the orthogonal the projection of Q into the theta eigenspace times key u is 0, but this is exactly the same as the length of this vector. But how is it possible? It means that the length of the projected vector is 0. So if I put this back into the definition of essential path, I should get 0. So that's a contradiction. Okay. So basically, we just proved that whenever we have an essential path, both endpoints has to be essential. Okay. The next lemma is okay, but what happens if we have the opposite? We have two vertices, and any path in between them is not essential. So for any of them, this product, so any path what I am taking between u and v, this scalar product will be 0. What's happening then? I'm claiming that if you delete one of the vertex, so you delete vertex v, then the size, the weight of the atom at u could only increase, okay, cannot decrease. And okay, to prove that, it's again it's quite simple after we turn into the right language. So if we consider the condition that any path between u and v, we don't see an atom, it means that the right coordinates in this theta eigenvector, we see zeros. Okay. But what does it mean? It means that if I would delete the subtrace below vertex v, the remaining vector will be a theta eigenvector for the path tree of g minus v. Okay, and I will denote this restricted part of the vector to be W. And from here, it's a simple calculation to show that using this W, that the atom at g minus v of u is bigger than equal than in g. Okay. So again, here we use the spectral theory that helps us a lot. So to be more combinatorial from here, it's much easier to say. So what do we have here? So what kind of structure we understand right now? We understand that whenever we have in a graph an essential vertex and a non-essential vertex, okay, what does it mean? It means that whatever path I'm taking in between them, it cannot see an atom, right? Because that was the first claim what I told you, that whenever you have a path that sees an atom, then both endpoints have to be essential. So if a priori I'm assuming beforehand that one of them is essential, the other is non-essential, then any path is non-essential. Therefore, if I would delete the non-essential vertex, what I will left with is still an essential vertex. So because the atom can only increase by deletion. Okay, so we already obtained one of these stability results. So if we delete any non-essential vertex, essential remains essential. Also, with that, we can see that special vertices has to be positive vertices. Why is that? Because the definition of special means that the vertex is not essential, but it has an essential neighbor. If I would delete that vertex, then the essential remains essential. So by definition of positivity, it means that we see that there is already essential vertex in the deleted graph. So it has to be positive. Okay. And you can believe me that deleting any special vertex doesn't change the type of the vertices. So this is the lemma. So far we only see that if we delete special, essential remains essential, but I'm claiming that it's more true. It's now easy to put together all the pieces on your own. Okay, so what you have to bring from the stability part is that deleting specials doesn't change the type of the vertices. Okay, what about the total change of the weights? For that, we have this nice lemma, which is quite technical, and apparently it is it's a nice application of Christopher Darboux identities. But right now you can see something which resembles their names. So someone is positive if in the deleted graph, so if I delete the vertex, positive vertex, then the change of the atom, if I add them up in the whole graph, it will be add up to 1. Okay, so the total the total atom can only increase if I am deleting a positive vertex. Okay, if I am deleting a neutral, the total mass doesn't change. And if it was essential, then it will decrease by -1. Okay, so this is the main lemma that understands what's happening with the total weights of the atoms. So now I would like to give you so relying on these two pillars, what I just told you. So deleting special vertices, the graph, the vertices doesn't change types, and also depending on this nice formula for how does the atoms changes by deleting a vertex. Using these, I would like to show you that in any infinite connected vertex-transitive graph, there is no essential vertex. Okay, how to prove that? First, we'll prove the first lemma. So assume that we have a graph G such that every vertex is essential. Okay, that's critical. Okay, if you feel like, think about it as a factor critical graph. Every vertex is left out in a maximum matching. Okay. What I would like to claim is that if I am deleting any vertex of this graph, everyone will become non-essential. Okay. Again, in factor critical sense, it means that after deleting a vertex, the remaining graph has a perfect matching. So why is that? So assume that V remains essential by contradiction, assuming for sake of contradiction. So I would like to delete U, and I'm seeing that V will remain essential. I will try to use the colors. So what does it mean? So if I am deleting U, all of his neighbors is non-essential. Okay, why is that? Because we know that U was essential, so not positive, and positive had the property that if you delete him, his neighbors, one of his neighbors became essential. Okay, so we know that all of these neighbors are green. Okay, so in particularly in the connected component of V, there has to be a special vertex. There has to be a vertex that is not essential, but it has a neighbor that is essential. Okay. Now, what to do? We delete W. What does it mean? It means that we deleted a special vertex, so it doesn't change no one's type. In particularly, all these greens remains green. Okay, green means non-essential. Okay. On the other hand, what do we have? So we this first product is the atom at theta. So since U was essential, this is a positive number, positive finite number. And this second, so we delete U and then W, and we are looking this quotient, what you can recall from definition of positivity, we know that this quantity is a negative finite number. So we know that this product has to be a finite number and non-zero. Okay. Now we are deleting in different order. We are deleting first W, and then we are deleting U. Okay. So now I use the first lemma for stochastic transformations. So we know that W was essentially in the original graph. So this first member here is again a positive number. How is it possible that this limit is a finite number? It's only possible if U is a blue vertex. It's a positive vertex in G minus V. Okay? So U is a positive vertex in G minus W, but we just proved that if I delete a positive vertex, one of his neighbors has to become an essential. So a priori, it means that out of this V1 Vk, at least one of them has to become an essential in G minus W minus U, which is the same graph as G minus U minus W. Okay, so that's a contradiction. So we just proved the generalization of the Gallai lemma. And now we can say what is the proof for the infinite vertex-transitive graph. So I'm claiming no vertex is essential. For the sake of contradiction, assume that everyone is, there is an essential vertex because it's a vertex-transitive graph. It means that everyone is essential. So it's a factor critical graph, and this is what we covered in the previous lemma. So in a factor critical graph, if I delete any vertex, no one will be essential. Okay, so it means that if I would delete the vertex U, then for any V, the atom has to be 0 at theta. Okay, and now we use the second main tool, what I described you as what is the total change of the atoms. So I just recall that. So since we know that U was essential, so it means that the sum of the changes of the atoms has to add up to -1. Right? This is what that was the second pillar. And you know, this member here, we know that it's 0. So this is the same as saying that this is -1 times this quantity. But we know that V was essential. Okay, it means that this number here is a non-zero number. And since it is vertex transitive, everyone is the same. So the right-hand side has to be -infinite. And that's a contradiction. Okay, so now it's really easy to put together all of these pieces. And I think I showed you some. I showed you all the tools what we used, and also the main ideas how to go into these directions. So I think I left only with some open questions. So one interesting question I think is that, is that what can we say about in d-dimensional grid? Is every vertex is 0 neutral or 0 positive? We didn't get any answer. Also, we are interested in, is there any vertex transitive graph such that all the vertices are 0 positive? Why is that a question? Because it turns out that if you consider any vertex transitive tree, so you are taking any regular tree, then because they have absolutely continuous spectral measure, from that you can easily get that every vertex has to be 0 neutral. But to construct vertex transitive graph where everyone is 0 positive, that seems to be a harder question. And also I think it's a nice question. Is there any infinite connected zero critical graph? So I think this is the point when I would like to thank your attention.
Thank you, Feri. And could I ask everyone to unmute themselves and give a round of applause to our speaker? And if anyone has any questions, then please go ahead.
Hi there. I have another question, actually. Whoops.
Yeah.
Can you hear me okay?
Yeah, I can.
Yeah, so I'm just trying to like understand these measures a little bit better. So if if I understand correctly, your results are for also if the degree is not necessarily bounded. So just any transitive graph. So this is just some like crazy measure on R.
No, so vertex-transitive graph, you will have automatically a bounded degree. So.
Oh. I see. So there is some degree.
Yeah. And this is maybe I didn't emphasize. So for me, the graphs and what I am considering has a finite degree always.
Okay. Is that obvious? I feel like that's something.
They have an
maybe I should
absolute upper bound. Sorry. So there is an absolute upper bound for their degree.
And like, and what else is known about this measure? Like, is something known maybe that it's continuous would be a next step, or is there some hope that for a transitive graph it would be continuous?
Yeah. So it's so already this kind of question that so this matching measure was already used by for example by Chikvari to prove results on number of matchings in bounded degree cases to prove lower bounds, and if I recall well, he at some point he wanted to prove that if you know something more about the zeros around of zero, so if the matching measure around zero is absolutely continuous, then you can have much better bounds for the number of matchings or number of perfect matchings. I don't know which one right now. Yeah. So, for example, for Z squared, I think that's a nice conjecture. That's also a valid conjecture. And sorry, it's an open conjecture. Is that is the matching measure of Z squared or Z to the 3 is absolutely continuous at 0 or around 0 in a small interval.
I see. Interesting. Okay. Thank you. Yeah.
For example, there is quite a recent result, I think from this spring, when people proved that if you consider the universal cover of a finite graph, that will be a tree, and clearly not a vertex-transitive graph, it will be quasi-transitive, because it has only finite numeric types.
Right. Okay.
For those graphs, they proved that that it has only atoms and absolutely continuous parts. So it doesn't have that semi-continuous part.
Right. It seems like what would an atom mean? Is there any sense of what an atom would mean combinatorially? If there would be some like combinatorial interpretation of what an atom would mean.
I would be really interested also in more additional description of atoms other than 0, because for 0 it's quite easy. The atom at 0,
right.
in the local sense means that
Right.
Are you uncovered in a maximum matching or not? Or
Right.
how much vertices are left out? Yeah. Anyway, you can turn it around.
Interesting. Okay. Thanks.
Are there any other questions? So maybe there is let me say, a naive sort of thing I would try to do, and if you could comment on anything you see there. So suppose I have a Benjamin-Ishram convergence sequence of graphs, and with each of them I do say I am doing theta equals 0. So I'm just doing the ordinary Gallai-Edmonds theorem. And okay, and you have this decomposition, and some pieces of this decomposition. So I'm now, it can happen to you that you have some of these pieces will be bounded sized. So what I'm saying is that you can do statistics on these bounded sized components you get in this Gallai-Edmonds decomposition. So my question is whether you could have some sort of continuity statement that okay, and I guess you have to be very careful here, but if you have a Benjamin-Ishram convergence sequence of graphs, then in some sense, these statistics on these components converge, like the types you see on this factor critical.
Yeah. So we have, I show you this inequality at the start, which was, sorry, I will recover here. So this theorem here. This was the inequality. I think this is something like what you are speaking right now. So whenever you have a Benjamin-Ishram convergent finite graphs, then it will converge to a unimodular random graph. Okay, and basically there are some hidden statement in this one inequality. So first main sentence, now it is written out that if you look at the essential vertices and you look at the connected component of them, with probability 1 they will be finite. Okay. Moreover, so this is what is quite rational. So this is why we need unimodularity in order to say that this blobs will be only finite sized. In this way, this is the only way to say that the number of what is the number of connected components of essential, because you need some kind of bond on them. And basically, if you have some kind of nice expansion rate, what we were able to prove is that the size of these blobs cannot be any big. They are bounded, so the size of those graphs cannot be as large as you think. Sorry, so they have bounded complexity, to say that. So if you put more structure on it, we use this U. So I think this answers partially your question.
Okay. Yes. Thanks.
So there is some kind of statistics. Yes. So these will be nice bonded size graphs, finite graphs. So.
Mm-hmm. Yeah, so what I was maybe asking first was, if you have some Benjamin-Ishram continuity in the sense that, I have my sequence of graphs and all these factor critical components, or 93% of them are, I don't know, triangles. And then in the limit somehow, I also see 93% of these components as triangles.
Yeah, I think this is what happens. Yeah.
Okay.
This is what has to happen. So the decomposition itself has to be continuous, basically. Mm-hmm. Yeah, I think this should be true.
Mm-hmm. Thank you. Are there any more questions?
I have another question, if no one else does. So I guess my question is, what about for if we go to like a more general, like hardcore sort of setup or something like that? Is there some hope of controlling these atoms or saying something nice about this distribution as you have here? Obviously,
what do you mean?
Independent sets are.
Instead of looking the monomer-dimer model, we look at the hardcore model, or?
Yeah.
This is your question?
Yeah, exactly.
Yeah, in that case, we don't have this nice description, a nice description for these measures, because we already lose the main property,
right,
that the zeros for finite graphs, the zeros doesn't live in a real interval.
Yeah, but still somehow there's this complex zeros living in a disk. So it seems to be so interesting to understand that probability distribution.
The techniques cannot be generalized in the sense that the Stevens transform sees only the moments. So if you just write out the series of for a Stevens transform, so you are expanding around infinity, you will get back the moments of the probability distribution, right?
Yeah.
If the measure would be complex, what you will obtain is the holomorphic moments. And the holomorphic moments are not enough to describe uniquely a probability distribution. Here we really use the fact that the Stevens transform, that basically the same information as all the moments, is the same as saying an probability distribution in a bounded interval. If you move into the complex plane, you will lose immediately this unit. I'm not saying that it's impossible to do. It would be really great to do.
Yeah.
And also, just to remark that the holomorphic moments will converge in that case. So that's true.
They will converge. Yeah.
But
so I also have a clarifying question. So it seems to me, I didn't totally understand it, but so something that was interesting is, I don't know if this is fair to say this, but you sort of prove, you recover this decomposition, or Gallai-Edmonds decomposition in the finite case.
In finite case it is recovered, yes.
Yeah.
By saying that I told you that this is how you can start to play around. If I delete this kind of vertex, what happens with the other? If you play around all of this kind of stability, so this is the full table of stability here.
Right.
So there is a bunch of things that you can try. So you are deleting a special. What happens with the neutral? It remains neutral, and so on and so on. So there is a bunch of cases. There is one really annoying line, the false one. Sorry. So the false one is as you see, that's the first line which doesn't contain any star. It means that that's true. We can prove only for deleting only finitely many vertices.
Right.
And this is why we don't have the third bullet point in the Gallai-Edmonds decomposition, because if we delete all the special vertices, which could be infinite set, we don't know what happens with the neutrals.
I see. Yeah, I guess I'm just sort of a little bit curious if there's some sense in which that the magic of just this polynomial is like encoding the magic of some other aspect of matchings, something special, obviously being the Gallai-Edmonds decomposition. That's sort of what I was asking or getting at.
I don't know. So is there any, for example, any process? So as I told you, the Boltzmann random matching is a nice process that tells you information at zero. So
Right, right, yeah.
For the zero, we have the Boltzmann matching. Is there any nice, any nicely describable, nice combinatorial way to describe what kind of process realizes at different atoms? That's I think.
Right. Yeah.
I don't know what is.
I see.
What's funny, we know there is a decomposition, but we don't know what kind of random object is there, or easily definable process.
Right. Huh. Okay. Yeah. Okay. Thank you. Yeah.